All right. Hi, everybody. Let's get started. We will be covering transformers and graph neural networks today. My name is Abuzar. I go by Abu more often. I'm a TA for this course. And I have taught this lecture last semester, so I'm not a newbie at this. But I've tried to compress both these topics, or at least the theoretical backing of both of these topics enough, that we can finish it in 1 hour, 20 minutes. In case we don't, I'll find an alternative way to deliver the last, I don't know, 1/10th or 1/20th of the lecture to you guys, maybe in the form of a video or however makes sense. But yeah, with that, let's get started with transformers. Now, in the previous lectures, we have actually covered quite a bit of ground in terms of building up to a transformer. First of all, we covered what are query keys and values, this whole paradigm, and the attention paradigm, which lets us use every single encoder output while producing every single decoder output, right? It takes off the load from the final encoder state of the bearing to carry all the information so far, right? Which it obviously can't do faithfully because information gets lost as we go forward in time, right? Next, we also covered self-attention, which is probably the most important block for transformers here. And we covered what's the energy function, which is basically a scoring function trying to determine how important things are. And the attention function, which basically softmaxes these scores, and we get our attention weights. We also covered that RNNs, which are our traditional way of going through sequences, are very slow. And they are sequential. They can't be parallelized. And RNNs typically have very terrible memory, right? And this is where transformers really shine, because everything that happens in a transformer can be parallelized. So the training is super fast, right? Cool. We'll start with why we need transformers at all, right? In any kind of sequential processing task, especially in language, we want representations for each of our tokens to be dynamic or to be contextualized, right? For example, if I have two sentences, I like this movie versus I don't like this movie, the word like needs to have a different representation in both of these contexts, right? One of them is very positive, one of them is very negative in terms of my sentiment towards the movie, right? So things like RNNs are able to do this because we process things in some order and we're able to contextualize the representations which come out of these RNNs. But as we said, they are very slow, and RNNs by themselves have very terrible memory, right? We fix this memory problem kind of by using things like LSTMs and GRUs. We make it kind of less terrible, but they are still slow and they are still sequential. We can't do them in parallel, right? CNNs, which can also be used to process sequential data, can be parallelized, right? Every single layer of a CNN with some clever feature engineering can be parallelized to be happen in one go, right? But the kernels, once they are learned, or the feature extractors, once they are learned, are static. So we don't go through any change once we have learned them. What that means is every patch of information will be processed the exact same way, no matter when we do it once we have learned, right? So the dynamic aspect of it is lost. So transformers help us with these three attributes, which is parallelizability, good memory, as well as having dynamic computation all at once. Okay, before getting into it, there's something which I used to find very confusing, is why we call these three things query keys and values. Do we have any takers, any guesses on why we chose these words? Yeah. Mm-hmm. Mm-hmm. Yeah. Right. So that's my speculation, right? I don't think anybody knows 100% why they named it this way, aside from the people. But if you think about databases in general, you can think of them as sort of key value stores, right? There are hashes or keys which will store information, and values which will be the information itself. And when you want to retrieve some information, you'll write a query typically, and the query will look at the keys to figure out where I need to look, and it'll retrieve the values as the information, right? So in simple terms, or in terms of the attention or self-attention module, the queries are the things which actually do the attention paying work, right? The values are what are paid attention to, and the keys are the ones which help the query decide how much attention I need to pay to each value, right? And of course, the attention weights are the attention itself, how much attention I'm paying to each value. Right, so let's give an example, which is, this is a great example. This is a 5-token sequence. And the point is that there is this person here in red. And this person is wondering, how do I adapt to my context, right? I have some meaning of my own. The word this has some meaning of its own, but it needs to adapt to the things which surround it, right? So it figures out that there are these nice people in blue who are willing to help. They say, look, this is my information. See if you can use it to figure out how you want to change your information based on what's around you, right? So, okay, my goal is to find a contextualized representation. And one way that I can do it in a very straightforward manner, since I have all this other information here, is to take a weighted sum, right? Pretty simple. But to do a weighted sum, I naturally need weights, right? I can't do a weighted sum without weights. So let's assume we have a set of weights, right? Which we will call attention weights. And once we have the weights and we take the information from all these people, we can figure out what our contextualized representation would be, right? So let's continue taking a few steps back. Let's say we have this black box magic calculator, which will take my information and it will take the information of all of my neighbors, and it will give me these attention weights, and with them I can find my contextualized representation, right? So let's actually do this, right? Let's put my information in, and let's put the information of everything else in the sequence also in this calculator, right? The goal is to figure out how important are all of these other tokens to me, right? And we do this by using our scoring function or our energy function, right? Which will be a simple dot product here. And we softmax it. We softmax it so that everything is between 0 and 1, everything sums up to 1, and there is no extra information going around here, right? And with this, we get our attention weights, which we can then use to weigh all these information, and we get our output, right? So cool. So we have a set of weights, and we have a bunch of values from all these other tokens around me. And I can just decide how much of each of these tokens I want, sum all of them up, and I get my contextualized representation, right? Seems pretty straightforward, right? Cool. So in this whole scenario, now the person is happy. In this whole scenario, the person who was looking for context was the query, was the one trying to look for information. The people who initially gave their information were the keys, right? And one query and all of the keys together helped us find the attention weights, right? And with these attention weights, we were then able to use these values, which are a different version of our keys, to find our contextualized representation. Right? Pretty simple so far? Cool. Any questions? Yeah.
I thought we get like a single key value, single key for each. This is a great example.
Yeah, we do, right? So all of these are separate keys.
But then if you're multiplying, like you multiply query with all of the keys
Yeah.
to get your values.
No, I don't multiply queries with keys to get my values. I multiply the query with the keys to figure out how important the value of that particular token is. Right?
Yeah.
We will get through a more structured example, but this is sort of like a storyboard format so that there are characters and we can sort of go through it. But in general, you use one query and all the keys to figure out how important are the corresponding tokens for each of the keys for that particular query, right? And then you use that information about how important they are, and then you use the values corresponding to all of those tokens to find what my final contextualized representation would be.
No, so what I'm sort of confused about is that the next words when you want to find is, the keys would remain the same, right?
Correct.
So
The query would change.
The query would change. Then is the query enough to give different weights?
Yeah, and eventually, so you'll, okay, so once we'll go through, I'll put your question on hold because we'll go through a lot more detail into how this works. But basically, we will learn how to put the query in the best form so that it is enough to figure that information out, right? Yeah.
Are there any non-linearities in the softmax? Softmax is
So softmax is a nonlinearity, right? But there will be other nonlinearities which end up in the whole process. We will have some NN dot linear layers which have nonlinear activation, so they'll end up being nonlinearities. Okay, cool. So with this, let us actually go to a more structured example. And here we have these 5 input representations of all of these 5 tokens. Now these representations can be literally anything. You have your vocabulary. You can make it one-hot encodings. You can make them word embeddings like word to vec or glove, or if you're using any other kind of data aside from MLP, you can use their embeddings which are present, right? But once you have them, the first thing you do right here is you pass each of these representations through 3 projections, right? One of them for the query, one of them for the key, and one of them for the value. And these are, of course, learnable parameters, right? And you do this for each of the 5 tokens, and you arrive at 3 sets of, or 5 sets of queries, 5 sets of keys, 5 sets of values, and each of them are in the dimensionality that the model requires them to be, right? That's what the projection does. Cool. So we do this for each of the 5 tokens, and we have, as I said, 5 queries, 5 keys, and 5 values, right? Then what we do is we take one query, as we did before, we take one key, and figure out what the energy score would be for this particular query key pairing, right? We take the same query, a different key, and figure out what the score would be for this pairing, right? And we do this a total of 5 times, and with this we get an energy vector, right? We pass this energy vector to a softmax, just as we did before, and from this we get 5 attention weights, right? It's 1, 1 or m, n for how important is the nth token to the mth token, right? And we'll use the shorthand going forward. Okay, cool. So we have these 5 weights for our first token corresponding to the 5 tokens which are present in my sequence. Cool. So what do we do next? We have our weights, we have our values, and all we do is we just take a weighted sum, right? We take the weights, we multiply them with the value vectors, we sum all of them up, we get one vector which is of the same dimension, and we get our output representation, right? It's the same story, but in a little more structured format. Yeah? Cool. So this was the attention. Yeah?
I may have missed this, but what is the importance of the value vector here?
The important value vector here? The value vector is what gives the information to be used.
Okay.
So just semantically, key tells you how much important you need I am to you, and the value is the thing itself, which is XYZ important. Yeah. Cool. So we did the attention mechanism here, and specifically in the paper, which is attention is all you need, which introduced this concept of transformers, used what's called as a scaled dot product attention, right? And let's break this down just a little bit. The word dot product because we're essentially doing a dot product of queries and keys here, right? We use the word attention because we are calculating attention scores. And the word scaled comes because we have this term which is square root of dk, which is the dimensionality of my keys. And any takers on why we do that? Why we scale our energy, which is inside the softmax? Shot in the dark, maybe a wild guess. Cool, we do it for, yeah.
Maybe a proper normal distribution of the dot product.
Realistically, you can give me any reason and it'll be fine. Honestly, the answer is simply for numerical stability, right? They tried a bunch of things and this worked the best because they wanted numerical stability, right? Okay, cool. And finally, our output for the ith token is, again, a dot product of alpha and the V matrix, right? This V matrix is basically you are stacking all of the value vectors together, yeah? So obviously, they're all just dot products and all just vector operations, and they can always be parallelized, right? And this will be a common theme in the transformer section, that there will be a giant poster in yellow which says it's parallelized, okay? Cool, so let's take a short example to make sure that we understand what's happening. Yeah?
What are the value vectors?
What are the value vectors? Okay, so the value vector is, so you have these, one second, we have these input representations, right? And we have the 3 projection matrices as well, which are learnable parameters, which will project my input representation to a query representation, a key, and a value representation. And over the iterations, we learn them such that the semantic meaning of query, key, and value is sort of brought out of these input representations. So the value is what gives you the information that you need to actually contextualize. And the query and the key combination will let you figure out how important it is. Yeah? Like you can ask as many of these questions as now as you want because this is like the core concept. Once you understand this, going through the math will be simple. Yeah?
Yeah, just in terms of the representation, for the second one, when you say for the second equation, it says
here?
y is equal to dot of alpha I, comma. What do you mean by v1 to 5?
So
Alpha I just multiplying with vi.
So when you multiply, okay, so alpha 1, 1 here. So this is like super important if you guys are not clear on this. Alpha 1, 1 tells you how important is the first token to the first token, right? 1, 2 is how important is the second token to the first token, right? And so these are the weights with which you will use the values of all of these tokens. So token 1, 3 will be combined with value 3, right? The value vector for the third token to figure out how much this contributes to my context, right? So which is why here we multiply alpha I. So alpha I being the whole vector, right? Which is alpha I comma dot essentially. So for the ith token, you have a full 5 length vector here. Yeah, which is why you're taking dot product. Otherwise, I would have just written like a
So
multiplication.
that represents the summation symbol on it. That
Correct.
is how
Correct.
it
That
is.
this represent the dot product represents both the multiplication as well as the summation. Yeah. Cool. And the reason why I haven't explicitly written what's the transpose, what comes on the left, what comes on the right, is because you can really change it however you like, as long as you're making semantic sense. But we'll get to the shapes in just a little bit. Okay, anything else before I move on to one little example? Cool. All right, so let's take an example. Let's say we have a 3 token length sequence, right? And just for simplicity, let's say the 3 projection matrices are the same for query key and value. So for each token, we just get a set of 3 identical vectors for the query, for the key, and for the value, just for simplicity here, right? So the first thing we do is obviously we multiply the query with the keys, right? And if we're trying to find the context for the first token, we will use query from the first token, and we will use keys from all of the tokens, right? And we do this dot product. We scale it by decay, which is 4 here, or root decay, and we get these 3 energy outputs, right? So we have a vector, we have an E vector, which can be softmaxed to give us a set of attention weights, right? So alpha 1 represents what is my attention vector for the first token. Cool. Then we take this dot product here for alpha and the full V vector, and it will give us a output vector, which is 3.99, 4.99, 8.99, and 1. Right? If you notice, the alpha vector here just kind of says that for the first token, the second token is super, super important, right? Because I'm taking 99% of my information is coming from that one, and everything else is really tiny. Yeah? Cool. So with this, we can move on, and for saving some space, we will use like an implied softmax here. And what's happening is we're creating a 5 length vector at each step. Okay, so we've compressed all of the computation we did before to this one little step. All right, so notice that alpha 1 is of shape 1, 5. So now we'll be introducing some shapes so that we are consistent in our calculations, because we'll be doing some matrix operations at some point. Yeah? Okay, what we do next is we take another dot product, right? We take all the values with these attention vectors, and we figure out what my output is. Right? The output is of shape 1, dv. Cool. We do the same thing for all the 5 tokens. And there we go. We have a full set, a full 5 length vector of contextualized representations for every element in my sequence. Cool. One thing to note here is the reason why we are doing this sequentially is just for visual effect. It really happens all in parallel. So you go up this computation chain in one step for everything in the sequence, because we have everything, right? Cool. And as before, this is the self-attention module, almost, but this is where most of the heavy lifting has been done. Okay? And as I said, a giant yellow poster which says it is parallelizable, right? And these are matrix equations for doing this self-attention, which is you find your attention vector A, capital A, using softmax of the dot product of query and the key vector, and you divide that by dk. The dividing by dk is just element-wise. You can do it anyway, right? And then you just do a dot product of A and V. Yeah? Yeah.
In this process, aren't we using the positional values of each? This is a great example. If I swap values, still all the values will be.
Yeah, true. At this point, we haven't done anything for the order. At this point, the transformer doesn't care. It's looking at it as if, okay, I'm here, and these are the things around me. I don't care where they are around me. I just know that they are around me, and I'll do what I can with them. Yeah.
Oh, so is the positional encoding not added before it passes through all of this?
The position encoding, we'll get to it at the later half of the transformer section, but the position encoding is sort of an additive feature to a transformer so that it knows the order. But we'll discuss it later. But good point. One question here. So the attention vector that we form is n cross n, right? When we did it for one token in the sequence, it was 1 comma n. But when we do it for all n of them, which is we use all n queries with all n keys, we get an n by n output, right? So what would really happen if I change the computation of my output here from AV to A transpose V? The shapes work out, right? N by n times n by dv. Is there any change, really? Okay, how many think there would be a change? Okay, how many think there won't be any change? All right, I'm guessing the rest of you are waiting for the others to answer. Okay, anybody who said there would be a change, can you tell me why? Yeah.
As opposed to previously where you'd be multiplying it with, say, the weights of each different word, now you'd be multiplying it with the weights of the same word.
Yeah, exactly, right? So it semantically changes what you're doing, right? So instead of doing it for every token, I take all of the weights and I multiply each of the values with those weights. What I would do instead is I would take all the weights and I would multiply the tokens with the tokens, right? So in deep learning, we often just tend to make the shapes match and it seems to work out. But it works out in homeworks because we make it so, right? In the real world, you need to understand that there is some semantic meaning to each direction or each axis of your tensor or of your matrix, right? You need to make sure that what you're multiplying makes sense for it to be multiplied, right? Okay, cool. The batching would be done in some extra slides later. If we have time, we'll go over it, else you can see it in the slides. But we have a self-attention module, right? This is called as a single head attention module, and we'll get to why it's single head. But before that, we have a short poll, right? This is 1125, and let's say we give you a minute, a little less than a minute to finish this. All right. Any takers on the answers? Louder. P and D. Yeah. This is really important for you guys to understand. If you got this wrong, please make sure that you understand that to calculate the contextual representation of the ith token, I will use the ith query and all of the keys, right? And also, please also understand that the projection that we do is learned, right? As I said before, it's not something you just fix. Yeah. Cool. Let's move on. So for now, let's assume that our input representations were, let's say 300 dimensional, right? Which is typically the scale of what you'll get from things like glove or word2vec. And for now, the way we're doing all of these dot products of everything everywhere is sort of assuming that all the information is everywhere and it can be mixed with everything and we'll get our context out. But it is possible that there is some amount of localization of information, right? It's possible that out of those 300 dimensions, the chunks of 50 sets of features sort of have information which is mutually exclusive to each other, right? And if we just mix everything, it'll get colluded. And so what we can do is we can split our input into k equal parts, right? Pass each of the k parts into their own self-attention module, get k outputs, and we can concatenate all those k outputs together to get our new set of contextualized representations, right? What would happen here, or what we hope to see happening here, is each of these k heads of my attention module are looking for a different relation amongst the tokens, right? In terms of, say, language, one might be looking for subject-verb agreement, one might be looking for a dependency parse, or things of that nature, right? Different ways in which the elements are related to each other, right? And this gives us a multi-head attention. Yeah?
So we just split the input vector into, let's say, chunks
Yeah.
of 50, right? What if the first 50 have some connection with the last 50 and like?
Yeah, exactly. That's a good point, right? So coming to what you just said, multi-head attention does give you a bunch of benefits, theoretical benefits, what we hope to see. But it does have some very strong assumptions, right? One of them is A, the information is localized, is an assumption to go. And the second one is these chunks which you separate don't have information which is required to compute the other one, right? It's possible that the first 50 and the second 50 have information which is so highly correlated that it can just give you redundant information. That's one possibility. B is that to make any sense of these 50 chunks, we need the other, right? It's entirely likely that this happens and we don't get any sensible thing whatsoever, right? So you really have to tune the number of heads that you want. Typically, if you make the heads too large, one of the two things will happen. One, you'll get redundancy, or you will get chunks which are too small to really have any informative things on their own, right? So you have to find the right number of heads. But typically, anything between 6 and 8 tends to work in language terms, yeah? Okay, any questions so far?
What do you mean you need the other? When you say when you were explaining the problem?
The problem? Okay, so I don't have a blackboard here, but let's say I have, instead of 300, let's say I have 100 features, right? And I break those into chunks of 50, just 2 chunks of 50, right? But the information which is contained in those 100 features, let's say it's only and only the dependency parts of my sentence, it needs all of those features to figure out how the dependency works, right? We haven't ordered them in such a way that things are localized, right? But then if we need the other 50 to find what's in this 50, then we won't get any sensible information out. Or we might not get any sensible information out. Yeah?
So I don't understand. You said like if you have too many heads, you get like vectors which might be too small to actually quantify. Like, why is that necessarily a problem? Like, is the significance of one head important anyway? Like, doesn't it really matter as long as all of them are?
So here's the thing. When you do a dot product, you mix the first feature with, say, the 70th feature, right? It does get multiplied, right? And it's possible that the way these features have been drawn up, and we're generalizing here, the way these features have been drawn up, do not order them so that the first and the 70th one are together, but they are 68 features apart, right? Just out of how they were learned. So we don't want the fact that this is very highly correlated to the other one, and you need this feature to make any sense of this feature, right? So if you end up separating them and you do individual computations, it'll end up making things harder for you to make, for the model to make semantic sense out of it. It could still work, right? I can't give you guarantees here that it will or won't work. It's just that this is a possible problem that you should be aware of. And if you see a trend, which is, all right, I have a transformer here, it's wonderful, it's a ginormous model, I have lots of data, but it's not really learning anything. So this might be one of the places you might want to look at when you're fixing things.
And I guess just to follow up to that, so you said like each head is sort of like one type of relation, right? Essentially, is that just like trying to make sense of the math, or is that like?
It's mostly trying to make semantic sense of what's happening. People have observed that when you try to find one kind of feature in one head, it is unrelated to a different feature in a different head. Some people have also found that the first and the 8th head found something exactly the same, right? So yeah.
What was the motivation behind doing it? Did it empirically work better, or was it just?
It did work better. It did work better. I think the way they went about it. So in papers, it's hard to decipher whether the thought or the experiment came first. But here, at least the way it worked is they wanted to see if there's any localization of information in word-to-vec representations. And when they did this, because they figured out, okay, how's one way to test this hypothesis is, let's say we just break it up into a bunch of chunks. And if you do individual computations, it should ideally figure out what's in that individual chunk, and it worked better.
Is the computational efficiency? I mean, this would be k factors faster, right? So.
Well, depends on how you parallelize or your parallelization extent. If you parallelize each level of my dot product at one point, it's still the same. But if I parallelize the k computations along with parallelizing the dot product, it would be k times faster. Yeah.
So is this equivalent as a batch size of k, or is that another dimension?
Batch is a separate dimension. Yeah. In what do you say? In transformers, when you batch your queries, one sequence does not interfere with another sequence within the batch. Aside from the fact that the weights are learned, right? The only way one sequence interacts with another sequence is through gradient updates. But otherwise, it doesn't interfere.
And batch norm as well.
Yeah. But batch norm is once again learnable parameters, right? The sigma and the mu are learned. So it's once again through updates that you figure out what's happening. Yeah. Okay, I'll take one more question before we move on.
Do the different attention heads have different weights?
Yes, they would be learned separately. Simply because, okay, I set them to something random, right? But eventually with gradient updates, they get learned different things because of how the gradients are flowing. Okay, let's take just one more. I saw you raise your hand.
Our one input is one word, right?
One input is one word in terms of language, yes.
So how do you split that word into k parts?
So
give the same word to k different channels.
okay, no. So I take a word and I use the H of that word, which is the input representation, which could be something like word-to-vec representations, which are already 300 or 600 long. So I split that representation into k chunks. Not the word itself, but I guess semantically you are splitting the word, but you're splitting the word in mathematical terms that I have this bunch of numbers which represent this word which I'm splitting. Okay, I will move on at this point, and any other questions you guys can either post in Piazza or get back to me after, and if we have some time, we can get to it. But okay, so this is the paper which gave you transformers, right? Mind you, it did not give you attention, although it's in the title. Attention came from Manado et al., and they did it on LSTMs, right? But this gave you a paradigm which uses only and only self-attention blocks, which is why you can parallelize it. Okay, so there are three major diagrams in this paper, which I think once you understand, you will get a grasp of what's happening in a transformer, really. So we've discussed these two, right? On your left is how a scale dot product attention works. Admittedly, we haven't talked about that mask yet, but we'll get to it, right? And on your right is a multi-head attention block, right? So these two, we are kind of, we understand what's happening. Cool. Then comes this ginormous diagram here. And this is, I think, why they're called transformers, because if any of you are familiar with the actual electrical transformers, the sort of coiling ends up looking like that, maybe. I don't know, I'm hypothesizing here. But this is what the main diagram looks like, right? So you have an encoder block, you have a decoder block. And once again, semantically, it works the same as the encoder-decoder things you've seen before, right? In homework 3 or in the lectures. So the encoder tries to figure out what the information is coming in, and the decoder tries to give you outputs one at a time. Okay. So let's go through what the different parts of this diagram are. So on the left, you see a multi-head attention in the encoder, which is the encoder self-attention block. And this is exactly the same as what you've seen before, right? Nothing fancy happening here. On the right side, the first thing you see is a masked self-attention block, multi-head self-attention block. And this is where the optional mask comes in. Now, I have said multiple times that decoders are, transformers are parallelizable. But can they always work in parallel? Right?
Not during output because they don't have all of the.
Right. Exactly, right? So decoders can be parallelized only during training. Well, the encoder is set already. So I have my encodings, but the decoders can only be parallelized during training. How do we parallelize them during training? Well, we just give them the whole output sequence at once. So if you go back to teacher forcing, right? Teacher forcing was every now and then I'll give them the output that I produced, and every now and then I'll give them the actual true output to decode further, right? This is just 100% teacher forcing rate. I always give them the right output. But this will lead to some amount of cheating happening. And what that means is, since an actual deployment, the transformer won't see what's happening. For example, I'm trying to complete an incomplete sentence. I can't tell you what comes after till you tell me what the next word is, right? So we want to make sure that the transformer also cannot see beyond the current time step, right? And each sequence, we had attention weights, which were n cross n. The simplest way to do it is just shut off the attention to anything after my own time step, right? How do we do that? We set them to 0. And in code, this could mean that you set the input to the softmax to -infinity, so that e power -infinity becomes 0, right? So essentially, in your attention output, the top half or the upper triangular part of the matrix would just be all zeros. Yeah, that's fair and simple. Cool, and this ensures what's known as the autoregressive property of my decoder, that I'm going in the sequential order which is already present in my data, right? I'm not violating it. Okay, this brings us to the second part in the decoder, which is a cross-attention block. If you notice, the 3 arrows going in, which are the query, key, and values, come from 2 different sources, right? 2 of them are coming from the encoder, 1 of them comes from the decoder. And since the decoder query is what actually pays the attention, semantically it makes sense for the decoder to give the query and the key and the value to come from the encoder, right? And this makes it a cross-attention block. This is what we were doing in terms of LSTMs in previous lectures, right? And the decoder input pays attention to the encoder output, right? Fair and simple. Okay, so here we have these feed-forward layers. Their entire purpose is to give you some more high-dimensional computation, to give you some non-linearities in your computation, right? And this is exactly the same as the MLP you had in the previous lectures. Yeah? Cool. Lastly, we get to these residual connections. Where have we seen residual connections before? ResNet. Why did we have it in ResNet? For gradients to flow, right? Here, there is another nice little semantic meaning to the residual connections, but they do allow you to have better flow of gradients. This, you can understand how the add and norm is working. It's just like a code beautification thing. I can just have one module which takes in my input, as well as what I need to do to the input before I add them and norm them, right? So that's what the sublayer is. So in, let's say in the first part of the encoder, the sublayer would be the multi-head attention. You would take the input, pass it through multi-head attention, add it to the input, and do a layer norm on it. Okay? Right, coming to the residual connections. So we've changed the O's to Z's to sort of say that we aren't done with our computation yet. We take the Z's, we project them once again into the output dimension, which would likely be the same as the input dimension because we need to do a residual add, right? We add this to our input, and we get our output, right? And transformers really, one way to look at it are as residual machines, right? So instead of trying to answer what will be my context depending on my sequence, they try to answer, okay, I know what my meaning is. How do I change it based on my context, right? I don't want to lose what my original meaning was. It's assuming that it itself did have some information, something valuable, but I just want to see how much I shift it based on what's around me, right? Going back to the previous example, the word like should have a positive representation initially, but then it shifts to being a negative representation once we get everything around it, primarily the word not, right? So it tries to figure out how much do I shift my meaning instead of just saying, okay, what is my new meaning, right? Yeah.
The attention is the shift, basically.
The attention figures out how much shift there is. Yeah. Cool. So now we have our output blocks, right? Cool. Now we get to position encodings, which you mentioned before, right? Transformers inherently don't really have a sense of order, right? They just use everything all the time. But this kind of loses the order, right? The order is kind of important in these sequences sometimes. Things like stock market information, things like language, there is an order which is important for you to figure out what the trend is, right? So we need to enforce this somehow. And we can just do it by giving it position encodings. What happens is you have an input. To the input you add, in some way, either concatenating or vector addition, the position encoding. And the idea is, okay, now the thing going into the transformer does have the information about the positions. And it can use it somehow, right? Okay, so we've seen this in the lectures, which is kind of bizarre and kind of difficult to understand what's happening. So we will try to make it a little simple. Okay, let's say our position encodings at this point are just one-hot representations, which is the thing at the ith position has the ith element as 1, everything else is 0, right? This is one way of saying, okay, this is where the ith token is in my representation. So what I do is I take this and I concatenate it with my representations. So my representation is H concatenated with the P, and now I have a new input, which can then be projected into query, key, and value, and yada, yada, yada. The same thing happens, and we get our outputs. So now we hope that our model now has an idea about what the order means in my input, right? This more or less brings us to the end of the transformer section. And yeah, with that, we have a poll. And you guys can take a minute for the poll before we jump into GNNs. Yeah. And we'll take some questions maybe after the poll. Right, in the interest of time, let's move on. The right answers are A, C, and F, which is the attention module tries to calculate the shift in the meaning. The transformer decoders can only be parallelized during training, and multi-head attention helps transformers find different kinds of relations between the tokens. Yeah.
So I had a question about the cheating thing.
Yeah.
So, like, yeah, it's not like traditional training, but other than that, is the concern like that will overfit?
The concern is that it'll start to use information which it won't have during inference. It's like during training, or let's say during, let's say in a different class where you are tested using exams, and each time I teach you, I give you the exact answer every single time. So you'll just not learn to use the information that you're given to come up with the answer. And then when I test you, you won't know what to do because you're used to having the answer given to you all the time, right? Kind of like that.
Just wanted to confirm the key and the value, sorry, the query and the value is sent from the encoder by the key is from the decoder.
No, the query is from the decoder. Remember, the query is what figures out how much attention I need to pay, right? And when trying to make a decoder output, the decoder state is what tries to wonder, okay, how important are all of the encoder states to me, right? So which is why the encoder states will give you the key value pair, and the query from the decoder will try to figure out how important is each encoder output to me and how I can use it to produce my output. Yeah? Sweet. All right, with that, let us move on to graph neural. Okay, I guess this is kind of important. So although transformers are amazing, they're really fast, they train really well, there are still situations where an RNN or something of the RNN family might perform better than a transformer. It's possible that the number of parameters that you have in a transformer are too much, or the data is too little for the transformer to really learn things well, right? In those cases, LSTMs are really an easy way to go, because also if your sequences are short, if you imagine, then there is not much to learn in terms of attention weighting, and the memory of an LSTM might just be enough to do it. So an LSTM might be okay for the job as well, right? So don't discount LSTMs and RNNs. Yeah. Also, in some cases, it might just be very difficult to transform a transformer to conform to your data. So in those cases, also LSTMs sort of provide a very easy way. Yeah.
Yeah, can we go back to the diagram of the transformer architecture? Like, I see that there are like n encoding block and
good point. So what this means is I just stack them on top of each other. So each time, so each output is of the same dimensionality, which is the dimensionality of the model, could be 256. And each time I give an output, I just pass it through another encoding block, and I pass it through another encoding block, and another encoding block. So what goes into the decoder is the output of the final encoding block each time. Yeah? And so I will have n decoder blocks stacked on top of each other as well, and each of those decoder blocks will get the information from the nth encoder block. You could, in theory, make it so that the nth encoder block gives information to the nth decoder block. That's just change in code that you do. But typically, the nx just means that I stack them on top of each other, and my useful output is what comes out of the last one.
So if like in the decoder, we are using different query, but the value and key is
exactly the same. Yeah. Yeah.
Just a follow up on that one. So when you're stacking the decoders on top of each other, you said only the so the last encoder is passing the key and the value. Last decoder block?
No, the last encoder block is passing this value to every decoder block. Every decoder block. So this thing that you see, including the cross attention module, is replicated n times.
Okay.
Also, because the input going into the block, which is the decoder block, is of the same dimensionality as what comes out of it. And only at the end do we have another linear layer which will transform it to the output number of classes that you want, for example. Yeah?
So the encoders all together with it being sent to every decoder block, and finally the last decoder block will be the one which will send the representations to.
Correct. Correct. Yeah.
So I think in the previous lecture, like only the decoder part was marked, and I think that was called GPT. Does GPT use only that bit and then
Yeah.
do the encoding?
So Hi guys, this is a small follow-up from today's lecture on transformers and GNNs. Given the number of questions we had for GPT, decoder-only models, encoder-only models, I thought maybe it's best to sort of make its own video so that there are no confusions. This video should be put at the end or in the middle of the actual lecture recording up on YouTube. So yeah, you guys can find this there as well, hopefully. Okay, so we're going to go over three things. One, encoder-decoder models for transformers, encoder-only models like BERT, and decoder-only models such as GPTs. And what we look at is the structure, the architecture, and how it works, not necessarily how BERT or GPT work, right? Okay, first of all is the traditional encoder-decoder setup. I've simplified the diagram here so that we only look at things which are important. And the task we look at, the sample task, is text generation. And the way it would be trained, or the way it works, is that you have some amount of context vector which tells you what you're supposed to generate. And these context or input tokens are fed into the encoder block. This encoder block then generates a context vector, which is then attended to by the decoder, right? So there is a cross-attention module in place. What happens in the decoder is you one by one feed in a token, and it uses the context vector or the fixed length context vector that it produces from the encoder inputs, attends to those, and repeatedly produces one output token at a time. And essentially, if we, perhaps the goal is, once we give it SOS, which is start of sentence, and give it 3 tokens, this is maybe we wanted to produce great, example, and EOS at the end. I mean, that's our goal here. So these are our 3 time steps for the goal vector that we want to produce. Right, so this is a vanilla transformer being used as a text generation model. Next comes an encoder-only model, such as BERT, and these are typically used for feature engineering or as part of pre-processing so that they can then be used, the features generated here can then be used for other downstream tasks. So the way it would work is you would take an input sequence, you would tokenize the input sequence, feed in those tokens into the stacked encoder blocks, which would then go through multiple self-attention layers, and then you would have a contextualized embedding for each of those tokens. And then you can do several things, like maybe you can predict on each token what part of speech that token is. Maybe you can predict on the whole sentence if you have another output token which sort of pools all the features for each of the tokens in, right? And these features, as I said, can then be used in conjunction with an MLE, an MLP, to do things like next word prediction, sentence prediction, or any other downstream task. Lastly, we come to decoder-only models. Now, the point is with these decoder-only models that there is no encoder. The encoder is never trained, right? All we have is a decoder. And here I've crossed off the word cross, and we only have self-attention modules. And the way it's trained to be a text generator is basically you feed it input tokens, and at each token it's supposed to generate what it thinks is the output token, right? So basically your input is shifted right, and you sort of prepend the SOS token here. At SOS you wanted to predict the first word. After the first word you wanted to predict the second word, third word, fourth word, fifth word, right? So there is no encoding, there is no context which is generated separately. All that happens is self-attention to all the current input tokens, right? So at each time step you would have one extra token which you can attend to, right? And this way it produces generated text. That's it. If you guys have any questions, please post in the Piazza post which contains this little video. And yeah, thank you so much. I will move on to GNNs now. I like that you guys are interested, but GNNs are also interesting, I think. And I don't think we'll have enough time to go over everything. Of course, please catch me after the lecture is over, and I can answer as many questions as you guys want. Okay. Cool. You guys can go through these extra slides at some point, and this is the batching shapes and how they work. But yeah, with this we come to graph neural networks. Okay. So far we've seen two major kinds of structured data, right? We've seen sequences like text and speech, where we use recurrent neural networks or some family of recurrent neural networks, or now we know we can use transformers here to process them. We also have grid data, right? Like images, which are strongly structured. All the pixels are next to each other. And we can use things like GNNs to find features from them. We can also use visual transformers, VITs, to find information out of them. But still, everything is very structured. And the models that we are using assume a lot of structure in it, right? But what about data like this, right? We have some bunch of molecules. We have some, what do you call it, social networks. We have 3D meshes of objects when doing 3D vision. So what kind of model can we really use? I mean, you guys know we'll use GNNs. But this is the motivation behind it, right? Not all data is structured enough to simply use things which assume structure in data, right? So let's do a little bit more of context setting before we jump into GNNs. What are graphs in CS and mathematical terms? A graph is typically a tuple of vertices and edges, right? Vertices being the nodes themselves, and edges being pairs of nodes which are connected, right? And in this example, we'll use what's an undirected graph, which means the edges are not directional. If an edge is there, you can go from point A to point B or B to A. It's just that the connection is present, right? And there's an example here which you guys can go through. But assuming we understand this bit, let's set a little bit more context with the concept of invariance, right? We have heard of the word invariance before. Where have we heard it? GNNs, right? And what kind of invariance was it? Shift invariance, right? Let's try to define it in mathematical terms to get like a robust understanding of what invariance is. So say we have a mapping, a function, which would be our model, f, which takes our input space to the output space, right? X to y. We have another mapping, which would be sort of a transformation, which takes the input space to another vector in the input space, x to x. If we can prove, and only if we can prove, that for all inputs x, f of x is the same as f of g of x, then we call f as being invariant to g. Right? Are we following the math here? It's pretty straightforward at this point. Okay, cool. So assuming that you are following it, here are a bunch of poll questions, which you guys can answer in, let's say, a minute. And the way you want to think about it is, you have a function f, which could be either argmax, Euclidean distance, or angle between vectors. G is some sort of transformation to the input, and there's some input space. And the question is f invariant to G? All right, answers. The first one, is argmax invariant to softmax?
Yes.
Yes. That's what we do when we're predicting, right? Is Euclidean distance invariant to shifting the origin?
Yes.
Yeah. Between two vectors, right? Of course. And is the angle between two vectors? Yeah? Think about it. If I have two vectors here, and the origin is here, and I shift the origin, the angle between them has changed, hasn't it? So I have a vector here and a vector here, and all I've done is shifted the origin so that the vectors are in a different place now. So the angle between them will change. I guess this is like a nuanced transformation. Maybe I can elaborate this enough for future slides. What I mean is that the arrowheads of the vectors remain at the same place, but I shift where they start from in space. So then the angle would change. Yeah? Thanks for asking that question, actually. I think I'll clarify this before posting the slides on the website. Thank you. Okay, so we have yes, yes, and no. Cool. All right, so the kinds of invariances that we've seen. So GNNs are kind of translation invariant, right? They're not mathematically translation invariant, but through the learning process, we learn the kernels as such that what we're looking for, if it's anywhere else in the picture, we will eventually have a signal which says, yes, yes, it's there in the picture. GNNs are obviously not rotation invariant by default. We can get to it if we have kernels which are rotated at each point and we learn all of them. But it's still not rotation invariant by default. Transformers, without the position encodings, are order invariant. Right? Doesn't matter what order I give the sequence to. If I don't have the position encodings, it'll give me the same output. It doesn't care. Okay. One more kind of invariance that is really important for GNNs is permutation invariance. And I'll give you a mathematical example before I tell it to you in words, because I think it might make sense. Okay, so say we have an original input, which is x1, which is a sequence of real numbers. Right? I have two more permutations of them, which are two different sets of numbers, but the same three numbers. Right? If I take an MLP, which is a one hidden layer MLP, which takes a 3-unit input, gives me a 1-unit output, would the outputs of the three vectors be the same? No, right? So clearly an MLP by itself is not permutation invariant. And what permutation invariant means is that for all of the possible permutations of an input, the output of my function should be the same. Right? This is a little hard to achieve, especially with MLPs because the weight matrices are set. Right? Okay. Any questions on permutation invariance? Awesome. Okay. So let's also set up a toy problem that we want to solve. Right? Say we have something known as an ionic liquid, right, which are found to be great solvents for carbon dioxide. Right? And the way we want to study them is we take the two ions, the positive ion and the negative ion, and the information is enough for us to figure out what the solubility would be of that. But we don't want to go through the painstaking process of doing chemical tests and figuring out what the solubility actually is. Maybe we have some data which has information about the molecular structure of the ionic liquid and the solubility as the label. Right? And we want to learn a deep learning model which will map these two, map one to the other. So essentially, we want a function which maps from the molecule space to a real number space, which will give you solubility. Yeah? Cool. So we have two questions here. Before diving into GNNs, can we use something like an MLP or a CNN to get good enough features that we can use? Right? Also, what are the kind of desired properties that we want in the model that will help us actually do this? So obviously, the short answer to the first question is not really. Right? And let's see why. The way you will use CNNs for molecules would be obviously you take some sort of input map, which would often be an image. Right? So I can give you images of molecules themselves. The images can be artificially generated as well. They could be labeled whatsoever. You take those images, you pass it through a CNN, and you get some sets of features, which you can then classify. Yeah? What if I rotate the image a little bit? Of course, the output would be different, right? And there is no telling that my molecules will be oriented in the same way all the time, right? They're very stochastic. I can't always fix them to be a certain way, and I take the perfect image and I make a data set. Yeah? So the outputs won't match, right? And it won't generalize. It'll only be fine for standardized images, and we won't get standardized images out in the wild, right? Because CNNs are not rotation invariant. Okay, let's see if we can use MLPs for it. Yeah? We already know that they're not permutation invariant, but let's say we change the data slightly so that it could be, possibly. Right? So what do we pass as input? With this, we get to get back to our definition of a graph. Say we have this undirected graph here, which is a set of vertices and edges, and we'll use this graph a bunch of times going forward. There are two things that we'll need from it, right? One, we'll need information about the nodes themselves. In the molecule case would be what is the feature for each atom, maybe, right? How many of them there are, et cetera, what are their properties. And we'll also need information about their connectivity, right? Okay, what can we use as connectivity information?
Like we can have a matrix of like zeros and ones where ij, if it's one, represents I is connected to j, and we can flatten it and like give it as a feature.
Sweet, awesome. So that's how we can tell them connectivity. This is very similar to how we in the simplified manner we gave positions to our transformer, right? Okay, what about node information? Well, pretty simply, I can just have features for each of the node, which I've learned or I've created. And in case you're not able to decipher what the colors are, there are some patterns here which you can maybe map to the letters and see what's happening. But we have this node information matrix, which would be n cross f. N is the number of nodes I have. F is the feature dimension that I have. And I have an adjacency matrix, which tells us what nodes are connected to what other nodes. And naturally, we can use these two as a combination to give information about our molecule into our model. One more important thing that we need to talk about in terms of graphs. Well, I guess before that, we can define a model which takes Rf and Rn and gives an output of Rd, where D is the dimension that we want an output in. Maybe we don't want to finish our computation. Maybe we just want to extract features for each molecule, and then we predict on it using an MLP maybe. Okay. So this is kind of important to understand. Let's say I have this one graph, and I have this one node information matrix, and I have this one adjacency matrix, right? Imagine what I do to it is I change the names around, right? Take the carbon dioxide molecule, for example. It's CO2. Let's say, just for fun, I start calling carbon as oxygen and oxygen as carbon. So it ends up looking like OC2, right? But the molecule itself is the same, right? Would anything about the molecule change? No, it'll still act the same way, right? A lot of it would still be bad for me, so on and so forth. So what that means is graphs don't really have any canonical order of names per se, right? So instead of changing names, what I'm doing is I'm changing the features around and keeping the names, like the order of names, consistent. But what I'm keeping constant is how a particular feature of a node is present relative to the others, right? If you notice, A is now this gray bunch of dots and not the blue slashes or blue lines. But the blue node is still connected to the black node, which is connected to the green and the red nodes. Similarly, the blue is connected to the black and red and green. So the relative positions of the colors of the nodes are still at the same point, right? So the graph, feature-wise, is still the same, right? And the question is, if I don't give you these graph representations and I only give you any one of these pairs of information and adjacency matrices, can you reconstruct the graph? Yeah. And will you end up with the same graph aside from the naming?
Yeah.
Yeah. So no matter what permutation of names and names I give you, you will always end up with the same graph as long as the information and the adjacency is the same, right? And that's the idea of not having canonical forms. So just to go through all of this text, basically what it means is if you have a set of information and adjacency matrices of any order plan of my graph, I will always end up with the same graph. And since the information that will feed into our models is in the form of a pair of information matrix and adjacency matrix, no matter how I permute it, I should always end up with the same output because I'm talking about the same graph, right? And this is where the permutation invariance in graphs comes in, right? So if I have m nodes, I will have m factorial permutations, and each of those permutations should talk about the same graph. And each of those permutations should give me the same output, right? Any questions? Yeah.
So in this case, instead of like constructing data for each node, let's say if you're just talking about molecules, right? You enumerate the set of atoms that you can have, right? And like have a one hot for the nodes, and then like basically an n cross n for the adjacency matrix. That should be permutation invariance.
The permutation invariance comes when once you do something with those permutations. It inherently just having a set of nodes is not invariant to anything because just having the set of nodes is not a function. The function.
So you have a set of nodes. So you basically still have two pieces of information.
Correct.
Which is that your molecule, what are the nodes that are there in the molecule? Because you still need to know that there is like let's say one carbon, two oxygen, and then your matrix, which is an n cross n, still tells you like what are the connections between like essentially those atoms, right? So that would still construct out to be the same irrespective of.
Correct. Yeah. Correct. It would be the exact same thing. All we would have done is instead of f here, the f corresponds to the total number of atoms that exist because you've made it a one-hot encoding. Yeah? That's all we've done. We've just changed what the feature is. Instead of it being a learned dense feature, I've made it a non-learned sparse feature. That's all I've done.
Right, but in that case, it doesn't change if you change the labels. because then it has a fixed label.
It never changed. That's the whole point. So here, even now, if I permute the names here and there, the graph that I have is the same, and it should always correspond to the same label. Right? If I call things differently, it doesn't change the solubility of carbon dioxide in that molecule just because I'm calling it something else.
Going back to the CNN thing, like even for CNNs, we do like the transformations to make it rotational invariant. Right? So why don't we apply like a similar approach here? Like why don't we just sort of simulate data to?
Won't it sort of become okay? I guess you could, right? But it would be how many orders of magnitude difficult would it be? You would need a factorial times more computations, right? It would be infinitely slower.
So is it just a computation that's actually not like that
Yeah.
would be a solution though?
Yeah, you can always brute force your way out of any problem, right? But brute force will not lead you to a good solution, which will always be able to generalize. What if at some point I discover a new element, and now I have to go from m factorial to m plus 1 factorial, and now my order of complexity also grows in factorial terms, aside from itself being a factorial point, right? So it becomes a massive computational problem. Okay. Right, so let's say we have this input and we've sort of simplified the features. Let's say the features are just a tuple of binary features. We take a whole set, a one row, and I give it to an MLP and I get an output, right? A traditional MLP, if I permute the inputs, will not give me the same set of outputs because the weights are fixed, right? So the question about what happens if we use a different order plan is just that changing the order plan will change the sequence order and thus change the output, which is not what we want. So an MLP, even if I use graph features, traditionally fails in trying to achieve permutation invariance. Okay. So the story so far is graphs can be represented using a feature matrix and an adjacency matrix. We have graph representations which don't have canonical order forms, and we have permutation invariance, which is a desired property in terms of graphs. Yeah? Okay. So let's try to understand how a single layer of graph convolution works. The reason why we call it graph convolution is because the paper which introduced it did graph convolution networks, which sort of fall under the family of graph neural networks. And the idea here is we use a birds of a feather assumption. What that means is things which are around certain things are similar to those things. It's kind of like contextualization. I'm contextualizing my nodes embeddings with whatever's around me, whatever I'm connected with, right? If you go back to CNNs, the way we did pixel convolutions and we look at it in terms of a graph, a grid can be looked at as a graph, right? So each output node, essentially what it was doing, it was pooling in weighted information from each of its neighbors, right? It had a self loop because I have a weight for itself as well, so I don't forget about myself, right? So you can think of it in terms of graphs, right? Now what's happening in a graph convolution is the exact same thing. It's just that we don't have an order anymore. And because we don't have an order anymore and we want to simplify a few things, we say the way I weight everything which is one hop away from me or one edge away from me is the same. Yeah? And 2 hops away is a different weight, 3 hops away is a different weight, and so on and so forth. So in essence, a node embedding can be defined by what's around it. And we want to learn a node feature by propagating all these information, which is where the word message passing comes in, if you heard about it in terms of GNNs, right? So we pass on the information from each node to everything around it so it knows what its context is. In hindsight, maybe I should have called this lecture contextualization because that's really all that's happening all the time. But let's say we want to generate node embeddings based on local network neighborhoods, and we choose this as the target node, right? So its immediate neighborhood would be made up of the things connected by these 3 red edges, would be C, D, and A. Right. So let's say what we do is we put all the nodes in place. We pool all the information in from our nodes. We do some processing to it, and we give it to B. And now B has information from A, C, and D, which are its immediate neighbors, right? But if we just do this, we've sort of forgotten about B itself. Right? Now all B contains is information about its neighbors, but not itself. Right? So to fix that, we sort of add this self loop, right? And semantically, in essence, maybe it works the same way as a residual connection, right? And now we have information from myself and all of my neighbors. Cool. But the question is, before the question, if you want to go 2 layers out, or if you want to have 2 hops away information, we just do the exact same thing one more time. with all of my neighbors. So as you see, the neighbors of A were A and B. The neighbors of C were B, C, and D. And what's happening is each of the nodes themselves are their own neighbors. So we have an implicit self loop each time. At this point, it's a good idea to tell you that this is how layers in a GNN work. So the more layers you have, the farther away you're going in terms of accumulating information, right? Okay. So what really happens in this gray box that we have here? In essence, it is a two-step process, right? First, we pool all the information in. It could be sum, it could be mean, it could be any other vector operation. And then we apply some neural networks to it, right? Could be a linear transformation with a nonlinear activation, right? Yeah. So, okay, before we move on to the math, any questions? Yeah.
Do the aggregate function here need to be like permutation invariant?
Okay, imagine I change the order in which the connections happen. I put C before D or D before C. If I'm just summing all of them up, if I'm doing a mean of all of them, does it really change anything?
No, but like is it required to be permutation?
Correct. If I end up putting the order into the information, then it will naturally become permutation invariant, which we don't want. So we don't want to give it explicit information about where it is. We don't want to give it spatial information. And this is, one second, this is like a key idea which I would have hinted at the end of the lecture. But if we give spatial information to these traditional GNNs, we lose our translation and rotation invariance as well. And to some extent, we might lose permutation invariance unless we explicitly tackle it, right? So to deal with it, we have these things called as equivariant graph convolutions, which are completely out of scope. But you guys can read about it if you want. Yeah.
So are all the A, C, D, and B, like, are they trained embeddings of like, or are they just random at this point?
Okay, we'll get to that. But if you go outside of layer 0, the way it works in any MLP maybe, the input is not trained, right? The input is what you give. And eventually, as you keep going up or deep, you start getting representations which are learned. The same thing happens here. Yeah.
While training, how do we generally do we cover all the nodes on the graph and start from D again, or do we just keep on going? Because there are a lot of cycles over there. So essentially, the graph will keep on going, right?
True. So depending on how far we want to go, we'll limit the number of layers. But once you look at the math, you'll understand how it stops its computation. There was one more hand which was raised here. Yeah.
I was wondering about, like, you're taking, so essentially you're saying each of the neighbors has the same amount of information.
Yeah, but its information itself is different.
Right.
Yeah. And we can also at some point take the edge weights into account, but I'll show you how that happens. We have about 10 minutes, maybe I'll take 12 minutes to at least cover the scalar form of the equation. And the matrix form, maybe I'll leave to a video or you guys can look at it. But okay, this is what the equation for the nth layer looks like. All right. I take everything from before and I pass it on to the L+1th node. HV L+1 just means what's the representation of the vth node at the L+1th layer. HUL means U is part of the neighborhood of V. And I scale it with the number of neighbors V has so that I don't just overly weight things which have many neighbors. Because if you think about it, if it has many neighbors or if it's connected to everything, it doesn't really tell you much, right? Think in terms of citation networks. If I have a paper which is connected to every other paper, then every other paper has information about it as well. It's not really that important. But if it connects to something which is really nuanced, it gives you that much more information. Yeah. And all right, so let's just trace all of these things back to our graph, and maybe what I'm trying to say will become more apparent. So these two things which are happening here, which is HVL and the HUL summation, talks about the pooling, right? And what we do with the weight matrix W and bias, or still a learnable parameter B, is what comprises of the two, along with the nonlinear activation sigma. Could be anything. And we do this for every layer sequentially. So the same thing happens on every layer, just that the learnable parameter is different. Once again, as I said, the sigmoid or a sigma is a nonlinear activation. W and B here are learnable parameters, right, at each layer. These summations are what the accumulation of features from neighbors are. And the HV here signifies the self loop, right, so that I'm not forgetting about it. Okay, this begs the question, how do we start? What is H0, right? I've written XV here, but what is XV? Can someone tell me? how do we get the first representation? How do we start?
The current representation?
Well, okay, yeah, the current representation, which is the initial node embeddings, right? At the 0th layer, I have done no processing. So I will take what I was given at the very beginning, right? So these are n cross f, and I will have f length embeddings going in. Okay, so let's see how this works out. And okay, we have enough time for a matrix form. And now you'll see how it works in terms of batching. Yeah?
So we start at some point, right? So it's not necessary that all the nodes will be there at that point. So the initial layer only has, like taking the molecule example, right? If say this is oxygen, these two are, this carbon, these two are oxygen. If you start from this layer, then you only have the oxygens at the starting layer.
So the way we go in terms of layers, the way we did here, and the reason why I was referring to this as a scalar operation is we only look at one node at a time. So if you're trying to find node embeddings for the carbon molecule here, we'll start from all its neighbors and accumulate information into carbon, right? If I have a larger graph, let's say the graph which we had here, right? If we want to find the information for the node D, and we want to find things 2 hops away, I would start with neighbors which are 2 away, accumulate into neighbors which are 1 away, and then those accumulate into B. So instead of going outwards, I go inwards.
Starting nodes are only the ones.
Correct. Yeah, we start at the outermost boundary and then we go inwards. And the reason why it works one by one is because we're doing it for one molecule at a time. But the moment we move to our matrix form, which I'll show in just a second, we'll just be doing everything all at once. Right? Yeah.
Is there a way to assign importance to different connections? Because
100% there is. So an adjacency matrix just tells you whether there is a connection or not. But if I alter it, and we'll see how the adjacency matrix plays into the matrix form, currently we can still weigh things differently.
Because carbon having one bond with oxygen is different with carbon having 3 bonds with oxygen.
True. Okay, so okay, let me say, let's not think about it in terms of chemistry for now. Yeah. But if you see here the summation that's happening, I'm going through all of the u's, right? For each n, I can also arbitrarily define a weight for each of its u's and just multiply that weight here. It's really up to you however you want to weight it. But in the traditional form, I'm just taking a regular mean. Okay, I can take a weighted sum. It's just that here all the weights are uniform. Okay. All right, so let's move on to the matrix form, which I think we can cover. All right, the first thing we want to do is figure out what the shapes of all these vectors are, right? We're going to say that through all the layers, no matter how far we go, we always maintain a f length vector for any layer representation of my feature, of my node, right? So my input, which is HU, or itself, which is HV, are all 1 cross F. My initial node embeddings are also 1 cross F for each node. And what I get out of it is also 1 cross F. So in terms of what we get as a matrix, instead of H, like the small h, we get a capital H, which is the matrix, which is a stacking of all HVs, right? For simplicity, I didn't change the colors here. Also, I didn't find too many colors to do. But point is, at each layer, if you stack all of them together, you'll get HL, which represents that Lth layer accumulation of information. Okay, let's look at the summation here, right? Clearly, we will need to use a node embedding, right, at each layer to get the HU of L. And we will use, all right, I showed it to you, but if you were to think about how we would make sense of the summation over the neighborhood of V, how would you do it?
Adjacency matrix.
Smart people. Okay, adjacency matrix. If we multiply this with the adjacency matrix, what happens is each row gets multiplied by all of the vectors. And since everything else is 0, I just pick up what is my neighborhood and I add them up. All right? Cool. We need to take care of the 1 over nv term, and we can just make a matrix out of it. It can be an identity matrix multiplied by 1 over n by v, which will have a uniform weighting for all the terms. We can change it, as you mentioned before, if you want to weigh them differently. Okay? And the last thing we want to do is we want to incorporate the weight layer. Yeah? And we make it an f by f and multiply it at the end. As I mentioned before, this is a learnable parameter, so you don't need to worry about what we set it as. We can set it as anything. It will eventually learn something. Yeah. And now our output that we get is n cross f, right? So the shapes work out. Yeah. But here's some food for thought, right? Why not multiply like this instead? Instead of putting the weight matrix at the end being F cross F, why not just make it N cross N and do it before the node computation? Aside from the fact that we'll have more parameters now, but let's say it's an arbitrary difference. It's not, it's a trivial difference. We don't need to worry about it. So why not do this?
Because suppose you want to add new nodes.
Yeah, one second, sorry. Yeah. Well, a lot of them would have been going to 0 anyway, right? Because the adjacency matrix is still there. So I saw one more hand raised way out at the back there.
I thought maybe because you might not be able to update the embeddings properly, but I guess you can still flow the gradients. So.
Okay.
It's gonna be permutation invariant, is it not? If we do on like weights on features instead of weights on the order of nodes that they come in?
Well, not really, depending on how you learn it. The adjacency matrix and the node information is what comprises the graph. And as long as how I'm doing it is invariant, it will still be invariant, most likely. Okay, okay, one more, yeah.
It takes more memory space.
Yeah, that's true. It does take more parameters. But the real reason here is that if I do this, what I'm doing is I'm mixing nodes with other nodes, right? The weight matrix of 1, 1 through 1n just takes what node do I want and how much do I want in node n's computation. It's like doing an attention vector on nodes but not features. So I'm only mixing node information. I'm not mixing feature information with each other, which I still do want to do. So if I placed an n cross n here, I'll end up mixing only node information, and I never end up mixing any feature information. So features end up being too independent of each other, and no amount of computation, cross computation happens, right? Okay, let's move on to this self-loop part. Again, obviously, we will need some information matrix, and we will need a B learnable parameter matrix, right? What do we multiply here, which is n by n, to get only ourself? Identity, exactly, right? The identity inherently signifies a self-loop. So we can use an identity matrix here. And with this, and we just call it A prime for consistency because we had A as the adjacency matrix there. But with this, what we have is a very nice matrix form of the forward graph. And as you know, once we have the forward graph, we can do backward computation, and that's all fine. But there is one way to condense this just a little bit, and it ends up looking somewhat like this, right? And I'll just take a minute. The hat over A comes because we merged the A and A prime, just adding the identity matrix to my adjacency matrix, right? And to account for that, and the fact that I've mixed WT and BT, like transposes, into one W prime transpose, simply because they're learned parameters, it doesn't really matter. I learned something well anyway. I need to account for a different D matrix, which becomes D hat. And I split it into being D negative to the power of negative half, I mean root D and root D, and then I multiply them together. Simply because if I'm splitting AB into being root A, I need to have root A be root A again, because how matrix algebra works out. But anyway, if this is too confusing, you can stick with the one in the middle. And with this, we have the forward equation for a graph convolution. Right? This poll is not on Piazza. No need to open your computers. But this is only there because I knew we would run out of time. This is only there for your information. I'll go through this question, see if you can figure out what the right answer is. Okay, let's take like 10 seconds. What do you think is the true statement? Anything else aside from C? Correct. It's only C. Right? Okay. Cool. With that, we come to the end of the lecture, more or less. A couple of final things for you to take home is that GCNs are largely used for feature extraction, and then we can use those features for different tasks. One of the tasks can be predicting nodes themselves, like node prediction about whether I am type of class A or type class B. I can do link prediction, which is, am I a friend of this person B, right? Does a link exist between two people? I can do subgraph prediction, which is I can figure out what a collection of nodes is, and I can do graph prediction. I can figure out what the whole graph means. Yeah.
So, like, how much of this goes into things that aren't so easily represented as graphs? So, like in the molecule example, or the friends of friends example, like those relationships are pretty easily summed up in graphs. What happens if you have like more general data sets?
Well, if you have things which can't be represented as graphs, then you would naturally not use GNNs, right? But in general, most data can be represented as a graph, right? And if you've done any amount of CS, you would also realize that a lot of problems can be reduced down to some graph problems, right? So graphs are really everywhere, and this is a good way to find features for the graph. Right, all right, see you guys on Thursday's lecture then.
Yeah, so